So let's now take a look at thermal interference in design. For closed-loop systems, the standard design methodology for collective coupled systems is usually implemented, considering all the boreholes connected together in one large system, and also using only one particular configuration with one distance between the boreholes, all boreholes the same depth, and one energy profile with regard to heating, cooling, and domestic hot water. In fact, in practice, we need often to design fields of individual systems where they are not coupled, and we need to account for the thermal effects between these systems, but every system can have a different heat pump, a different energy demand profile, a different number of boreholes, and different depths. This can be done for an apartment building where we have different heat exchangers for a number of apartments using the heat exchangers together, or each individual apartment having its own heat exchanger, for instance. Both systems exist. How do we do this? Well, basically we use a combination of the standard design methodologies and the thermal interference calculations in an iterative design procedure. So what we do is that we have a number of systems. For each system, we calculate the length in a standard design procedure, using the energy extraction and energy injection for that system and the configuration of the boreholes that are possible for that system. And then we get a depth, a length for that borehole heat exchanger field. We then calculate the thermal interactions for the surrounding, the neighbors, the temperature effects on all the combinations of heat exchangers, and we add the temperature effects calculated by this interference calculation to the actual design temperature that we've used. So suppose that on our system the neighbors have a thermal temperature effect of minus 0.5 degrees. We don't design for 0 degrees, but we design for plus 0.5 degrees to account for those thermal interactions. We do this a number of times until this temperature effect that we have calculated is sufficiently small, for instance, smaller than 0.05 or smaller than 0.1, the stopping criteria, and then we have a, let's say, design that we are happy with. An iterative design procedure is required. So here we have an example of a number of houses where we have houses that we're going to install, numbers 1 to 8, and a number of houses that are already existing in light orange, numbered 9 to 12. And in the little tables on the right, you can see that at first, after the first iteration, we have a temperature effect overall of all the systems together, which we can separate in a temperature effect caused by the existing systems and a temperature effect caused by the new system. So the existing systems on system 1 have a total effect of minus 0.46, and on the new systems themselves, so systems 2 until 8, have a total temperature effect of 0.94 Kelvin on system number 1. In the second iteration, the larger table to the right, we can see, that the design temperature is adjusted by a certain factor, and we add that to the design temperature, and then we get new temperature effects. For instance, now we have with system 1 a total temperature effect of 0.9. The existing systems have a temperature effect of minus 0.3, and the new systems amongst themselves have a temperature effect of minus 0.6. We do this a number of times until we come to the final solution, where again we have this little table. You can see the design temperature that we have to, let's say, use, 2.89 degrees for system 1, which is 2.89 degrees higher than our design temperature of 0 degrees, where we have the efficiency of the system defined at. And we can see that in this iteration, the adjustment still required would be 0.07 Kelvin. So actually what we see here is that we are very close to the design temperature that we want, and we don't have to go any further. We have done our design calculation, and we have a depth of all the systems 1 until 8 where we have the design temperature that we want to get the efficiency, and also with the existing systems, we don't have any negative thermal effects that are bigger than minus 1.5 Kelvin. So this is fully allowed by the Dutch law. Now, another issue would be the optimization of large-scale ground source heat pump systems. A new development with 50 up to 1,500 houses, not uncommon in the Netherlands, where we have several different installers doing little batches of houses. The whole project may be phased over 2 or 3 or 4 years. And also when we're doing it, we don't yet know what houses are going to be built exactly. So we do not know the energy demand profiles at this stage. What we can do, however, is to optimize the allowed net heat extraction rate. So we calculate for each lot how much heat can be extracted from the ground without having any negative effect between the neighbors. This means that we limit the designer of the system to a certain heat extraction rate, and how that designer accomplishes that. It can be by drilling deeper. It can be by having a better balance between heating and cooling. So how the regeneration with regeneration with thermal solar panels, how the designer does that is up to them. We can implement it, or it is implemented in the Netherlands in a ground source energy plan. And that means that if you want to have a permit, you are obliged by law to comply with the rules in this ground source energy plan. It looks a little bit like this, where at the end of the day, you get a map and a database of allowed heat extraction rates for every lot. You can see that small lots that are close together will have a lower temperature and hence a smaller allowed heat extraction rate, and larger lots that are on the edge of the planning area will be allowed a larger heat extraction rate because they have less effect on the surroundings. This in the Netherlands, the planning tools, we use ITGBES, again, the interference tool to calculate the temperature effects based on the finite line source correlations. And we have added to this a optimization procedure where we can do this kind of optimization of borehole fields. Also, we have the Pro tool to calculate the temperature effects where we don't have the limitations of the simplified tool. In Sweden, there is a slightly different approach. It's called Temperature Reduction 3000. It has been developed for the Stockholm area, where there are many closed loop systems available or realized, and further optimization can be done using this tool. In Germany, mainly for open loop systems, there is a tool for the planning of the efficient thermal use of groundwater. It has been implemented at the Munich area, and also here we can calculate distance between the wells, monthly extraction rates and temperature difference based on design data available for the different systems. In Austria, we have a calculation sheet for open systems based on the analytical equations, and closed loop systems based on a norm, the SEA 384-6. And again, you can find more information about this on the internet. Some selected references here, mainly for the Dutch situation that I have been discussing. Further references, please take a look at the deliverable 3.1 of the GeoBoost project, developed by the Technical University of Munich, which hopefully will be available shortly.